Dear students, last class we discussed about the various transmission line parameters such as the series resistance, series inductance, and shunt capacitance and shunt conductance. And for a short transmission line of length delta Z, this is the transmission line system model, which is driven using input voltage of V. It's a function of Z and T, and on the output side the voltage is V, Z plus delta Z and T. V is a function of these two parameters. And there is other parameters such as variable parameters are this current and this input current and output current. So these are the variable quantities, but these are invariable quantities. They never change with the time. Delta Z never change with the time, and the resistance, inductance, and conductance, capacitance, they are time invariant parameters. Now let us see that the two equations we are going to derive from this the circuit, which is a transmission line model, and we will use Kirchhoff voltage rule and the Kirchhoff current rule to obtain the transmission line equations. And let's see that. And if you take this network, here we can see that there is a voltage. So V of Z comma T minus, there is a voltage drop across the resistance. So if it is a resistance, the current is I, the resistance is R dash delta Z, the drop is R dash delta Z multiplied with I. So similarly here R dash delta Z, which is the total resistance, into I is I Z comma T minus, so the voltage drop across inductance. If you take the inductance, this is the current, and total inductance is L dash delta Z. So voltage drop across inductance is L dash delta Z into di by dt. So L times di by dt. Similarly, we are applying this here, L dash delta Z. Since I is a function of Z and T, so we are taking partial derivative. So delta I Z comma T minus this voltage drop, which is equal to V Z plus delta Z comma T equal to 0. So Kirchhoff's law states that the voltage drop across a closed loop is always 0. Now I am going to divide this complete expression with delta Z. So divide by delta Z. So this become, we can combine these two terms, V of Z comma T minus delta Z. So here there is a delta Z which will get cancelled. So this become, the next time become R dash I Z comma T minus, there is another delta here. So delta get cancelled. So L dash di Z comma T is equal to 0. Now I am going to apply the limit by taking delta Z is very close to 0. Then this become, see here, I am going to take this outside on this side. So this become, I am taking minus here, V of Z plus delta Z T minus V of z comma delta dt, which is upon delta z. Then I am going to apply the limit where delta z tends to 0. This is for a small section of transmission line, which is equal to r dash I function of z and t plus L dash partial derivative I partial derivative with respect to time. Now if you see this expression, we can see that this is a change in voltage over a length. So change in voltage over a length when delta z becomes 0 can be represented in the partial derivative form as this is equal to this term. Here we can see that there is a minus term here. This is the voltage equation of the transmission line. Now using the same transmission line model, we are going to obtain the current equation of this system. So for that we are going to apply, at this point we are going to apply Kirchhoff current law. The Kirchhoff current law states that the algebraic sum of current at this junction equal to 0. That means sum of the incoming current equal to outgoing current, or sum of incoming current and outgoing current equal to 0. So let's apply that rule. So the incoming current is this one, and the outgoing currents are these two. So apply Kirchhoff current rule. So what are the incoming current? This one is the incoming current, I z comma t. Why I am using the small letter I? Because I is a variable quantity, so which changes with the time. So I depends on here we can see that t and z, the length of the transmission line and the time. So this is the incoming current. So what are the outgoing current? There are two outgoing currents. One is this one, and the one is the current through this conductance and capacitance. So I of z plus delta z t, and this current. What is the current through the conductance? If you take this resistance and capacitance network, this is the current across which voltage is there. That voltage is this voltage, V z plus delta z comma t. So we know that current is V by R. So 1 by R is G, so I can be write down as V times G. So here V is T times G. What is the conductance? This one. And the current through the capacitor. What is the current through the capacitor? I equal to C times dV dt. Similarly, I equal to C times, what is C here? C dash delta Z, C times dP dt. Since the voltage is a function of Z and T, we are taking the partial derivative of So this is incoming current and these are the outgoing current. So incoming current equal to outgoing current, that is the Kirchhoff current rule. So let us equate incoming current I of equal to outgoing current. So these are the outgoing current. Plus the capacitor current. Now I am going to do a slight modification. I am taking this to the left hand side, so that equation become minus plus this is equal to the and the capacitor current. Now I am dividing the entire term with delta Z, divided by delta Z. So this become, I am taking minus outside. So delta is that it cancel, only conductance. Plus delta Z cancel. Now I am going to apply the limit delta Z equal to 0. So what is this? The change in current, which is upon a small change in length. So this can be written down as minus here partial derivative of which is equal to, we can put delta Z equal to 0 here, delta Z equal to 0. So this become plus so this is the current equation of the transmission line. So finally we obtained the current equation, and this is the voltage equation. Here we know that the voltage is function of the series resistance, the drop across the resistance and drop across the inductance. Whereas here we can see that the current component has two part. One is capacitor current and another is current through the conductance. So this is the the voltage and current equation of the transmission line, and the more about the other function related to this voltage and the current equation of the transmission line we will discuss in the next video.